So electron affinity. Electron affinity is kind of like the opposite of ionization energy. It is the energy change when a neutral atom in the gas state gains an electron. So we can write an equation that would look like this, some generic element, M plus 1 electron, and then we get a -1 ion plus the electron affinity. Now, electron affinity is much less predictable than ionization energy. Generally, it's negative, meaning it's exothermic. So that kind of makes sense if you think about the electron as an object, and I'm the atom, and I'm getting an electron, so I'm going to pay you for the electron. So energy leaves me because I'm getting the electron. But it can be positive. Some of the alkaline earth metals and all the noble gases have positive electron affinities. Why would a noble gas not want an extra electron? Because it's perfect as it is, right? I've got it made. I've got everything just right. You're going to give me an extra one? No, thank you. You have to pay me to take it, right? What about the alkaline earth metals? Do you think they're going to be happy about getting an extra electron? No, because they're pretty set on losing an electron, right, to become like a noble gas. So the trends in electron affinity are much less regular than other trends. About the only one we can talk about is that it generally decreases, meaning it becomes more positive as you go down group 1A. Other groups don't show a trend, but 1A does. Electron affinity generally increases, becomes more negative across a period. But again, there's lots of exceptions. Group 5 has a lower than expected electron affinity because that extra electron you're giving it has to pair up with another electron, and that's not so great. Group 2 and Group 8 have very low electron affinities because that extra electron has to go into a higher level. So in any period, though, the highest electron affinity would be a halogen, which makes sense because halogens want to gain an electron. When they gain an electron, they get a noble gas electron configuration, and that's a really good thing. So they're very motivated to get an extra electron. Here's just a table showing some of the actual numbers. So we do see a trend in group 1A, 73, 60, 53, 48, 47. Not much of a trend, but there is a trend. Here, beryllium and magnesium actually have positive. Nitrogen is positive. All of the noble gases are positive. Well, there, I showed it to you. This is more interesting. Properties of metals versus nonmetals. And some of this is just common knowledge stuff. If I were to hand you a piece of matter and ask you, is this a metal? Is this made out of metal? You could probably tell me correctly whether it was metal or not. Right? What do you look for in identifying a metal? Well, it feels like a metal, right? Often it's shiny, right? If you bang it on something, is it going to shatter into pieces? No. So these are characteristics of metals. They are malleable and ductile. So what malleable means is if you take it and hit it with a hammer, you can dent it, you can smash it, you can change its form. Malleable means you can take a hammer and pound it into a flat sheet. You can do that with metals. You can't do that with other things like sodium chloride or carbon or gases or something, right? Ductile means it can be drawn into a wire. So there's a good reason that wires are made out of metal, because other things don't pull into wires very well, and metals conduct electricity. So metals conduct electricity. They also conduct heat. They tend to be shiny or lustrous and reflect light. Their oxides tend to be basic, and they're always ionic. They form cations in solution. They lose electrons in reactions. They become oxidized. Nonmetals are sort of the opposite of that. They're brittle in their solid state. They are dull and non-reflective in general, electrical and thermal insulators. Most of their oxides are acidic, and they're molecular compounds, not ionic. They form anions and polyatomic anions, and they gain electrons, so kind of the opposite. So we're going to talk about trends in metallic character. And so again, I think of metals as being masculine, and we could make a list of stereotypical masculine qualities versus stereotypical feminine qualities, right? Does this mean that every nonmetal is dull and non-reflective? No. There are exceptions. These are general properties. And so when we look at the trend in metallic character, we're saying, well, how much like the stereotypical metal is this, right? And so you can think of that with people, it's like, well, this person is more masculine than this other person. They have more of those stereotypical qualities. Does that mean they're male at all? Not necessarily, right? Because there's this continuum, right? So metallic character, how closely an element's properties match the ideal properties of a metal. I think this is the easiest trend to figure out, because you can kind of do it with just some common sense in the periodic table. Although I know that common sense is sort of becoming a superpower, because it's just really uncommon to have that anymore. I keep forgetting that. Metallic character decreases as you go across a period. The metals are found on the left of the periodic table, and the nonmetals are on the right. And metallic character increases as you go down a column, because we find the metals at the bottom and the nonmetals at the top. I don't want to look at that one just yet. I like this one better. So let's say we were going across period 4. We're coming across. So over here, these are metals, right? And then as I go across, I get into semi-metals and then into non-metals. So there's a trend that as I go across here, I'm becoming more and more non-metallic. The metallic character is decreasing, right? It's just like almost obvious. What if I'm going down? Well, nitrogen is a non-metal. I'm going from non-metals through semi-metals into metals. As I go down, the character is increasingly metallic. Does that make sense? And then this one sort of shows this more with pictures. So here's sodium, magnesium, and aluminum. These things look like metals. And then as we come over here, these things are not looking like metals. Chlorine isn't even a solid at room temperature. That's not metal. Here, going down, we have a gas, this kind of funky looking substance, and then we get down here to bismuth. That looks more like a metal, right? So metallic character increases as we go down. Any questions about that? So choose the more metallic element from each pair, germanium or tin. Don't all yell out the answer at once. Tin, thank you. Tin actually is a metal, right? Tin can, right? Tin foil. We don't make it out of tin anymore. As we go down, you can actually see that line. Let's make it like this. Germanium is right on the edge of that line. There's the stair-step line. The elements that are touching that line, except for aluminum, are semi-metals. So we've got a semi-metal and a metal. The metal is more metallic. Gallium or tin. Well, gallium is over here. Not possible. So the trends there are opposing. not possible. And if we look at, the identification, those are both listed as metals, and they are equally close to the line, so yeah, we just can't really. Phosphorus or bismuth? Bismuth. Bismuth is way down at the bottom. Bismuth is actually a metal. Boron or nitrogen? Boron is more metallic. Both of those are non-metals, but boron is closer to the metal side of the periodic table. Okay. Here's a summary. This is a separate section, but I'm not going to make it into a separate video because it's really short. This is a summary of the periodic trends. Gives a real brief reason in here for the trend moving down, the trend moving across. So this can be a good thing to refer to. When you're doing problems, though, trying to predict which is more metallic or which is larger or whatever, try to think it out first, and then check yourself. And then if you got it wrong, figure out why, so that you can avoid doing that again. Any questions? Yes. Yes, you need to know all the trends. Any other questions?